Hello and welcome back to A Slice of Physics. We've talked about the fact that static friction can be a tricky thing to work with since its magnitude and direction change, and we'll take a deeper look at that in this example where you want to hold a book stationary against the wall. So our question says that you hold your 2-kilogram physics textbook pinned to the wall by applying a force at an angle of 40 degrees above the horizontal. And then it asks, for what range of forces will the book be stationary against the wall? The other piece of information that's given to us is that the coefficient of static friction between the book and the wall is 0.4. On reading this question, you may be confused about a couple of things, and you may also wonder if enough information is even given to solve this question. When you are in those situations, my advice to you is still the same. Go ahead and follow the steps that we have outlined in solving these problems. And even though the full solution may not be visible to you right now, as you work through the steps, it'll become clearer. So our first step always is to draw a picture capturing the situation. So here's my vertical wall. Here's the book. And I'm holding it up by applying a force in this direction. And the direction of that force is 40 degrees above the horizontal. And the question is asking for the range of this force for which this book will remain stationary against the wall. What does it mean by range of forces? Well, you know that if you hold this book too lightly pinned against the wall, it's going to slide down. So you need a minimum force to keep it stationary. And if you start increasing your force, at some point in time the force will become large enough to slide the book up against the wall. So that gives you a maximum force. And what the question is asking for is that minimum force and the maximum force, because anything in between, the book will be stationary against the wall. So here are our solution steps as always. We have done the first part already. The second one was to draw a free body diagram, which requires a catalog of forces. So let me draw the free body diagram of the book over here for the minimum force situation. Let's go around the book, and the first thing we see is this force that I'm pushing on the book with. And then as I go further down, I've got the contact with the wall, which has got potentially two forces, normal force and frictional force. And then we have the long-range force of weight as usual. So let's start drawing those. I've got my force. Remember, we always show forces beginning on the object, so it moves over to that side. So let's call that force F. And that's at an angle of 40 degrees. And let's call this F min because we're taking the minimum condition right now. Then our two contact forces were normal force and frictional force. Normal force always acts perpendicular to the surface, so let me show it like that. The frictional force acts parallel to the surface, so it's either acting up or down. To determine the direction of that, I got to see what the book is about to do. Since I'm barely holding it up against the wall, the book is trying to slide down, and the friction is going to prevent that intended motion. So the friction in this case is going to act upward, and that would be static friction because the book is not moving. And then finally we had the long-range force of weight acting on the book from the earth. Okay, that's our free body diagram with all of the forces that are acting on the book. And here's my x-axis. And here's my y-axis. Now I can apply my Newton's second law for equilibrium, which would be sum of x forces is 0 and sum of y forces is 0. So the forces in the x direction, the positive force is going to be plus F min times cosine of 40 degrees. I'll let you take a look at why that's cosine by practicing your SOHCAHTOAs. Minus n, because n is pointing in the negative x direction, equals 0. And then my y direction, I've got two forces in the positive direction. One is Fs, and the other force is F min times sine of 40 degrees. And then I got minus W because W is pointing down, and that also has to be 0. Now you can see that what's holding the book up against its weight is the y component of the force I applied and the static frictional force. Since I want to work as little as I can, I got to get maximum help from the static friction. So in this case, I want the static frictional force to be maximum static frictional force. To be the maximum static frictional force. So let me update that over here and over here in this equation. So let me start by putting things in that I do know in these two equations. I'm going to move over here. The first equation simply is F min times cosine of 40 degrees equals n. I've just moved n over to the other side, or added n to both sides. The second equation, you remember Fs max is nothing but mu s times n, so I can show that over here, mu s times n plus F min, which is what we're out to determine, sine 40 minus w, but I know w, weight is always mass times the acceleration due to gravity, so this is 2.0 times 9.8, and all of that equals 0. I know mu s, that was given to me as 0.4, and this n that's unknown, I can plug it in from the first equation. So I'm going to do that and get 0.4 times F min cosine 40. F min cosine 40 is the same thing as n, so I've just substituted that, plus F min times sine 40 minus that multiplication will give me 19.6, and all of that equals 0. Now I'm left with only one unknown, and that's F min. So if I factor that in these first two terms, I would get F min as a factor. That would be times 0.4 times cosine of 40 degrees plus sine of 40 degrees minus 19.6 equals 0. So all I've done is factored out F min from these first two terms. And now if I add 19.6 to both sides and then divide by this parenthetical term, I would get F min is 19.6 divided by 0.4 times cosine of 40 degrees plus sine of 40 degrees. And all of these are just numbers, so now your calculator can work this out and you will get an answer of 20.6 or 21 Newton. So that's the minimum force I need to apply to keep this book from sliding. Now to figure out what happens with the maximum force, let's draw the free body diagram again over here. So now my force has grown. It's still acting at a 40-degree angle, but now it's F max. I've still got a normal force that would be larger now because the x component of that maximum force is going to be larger. I've still got the weight as before, and I've got the frictional force. But this is where it changes. If I had the frictional force acting in the same direction, I would get the exact same answer. But now, with the force having grown to the maximum, the book is on the verge of sliding upward. Remember that static friction can adjust its magnitude and direction to prevent motion. So since now the book is trying to move upward, the frictional force is going to change directions and act downwards. Fs is going to be acting in this direction. And since I want to get the maximum condition, I want the force that I can keep growing to before the book just is about to slide. And so that condition also relates to the Fs max. I want the maximum static frictional force that is stopping the book from sliding. The rest of the process would be the same as before. I've still got to do my conditions of equilibrium, so sum of Fx equals 0, sum of Fy equals 0. The x equation still remains the same, so it's F max times cosine 40 minus n equals 0, and that just gives me a value for n as F max times cosine 40. Now note that the normal force is changing between these two situations as the force that I apply changes. Normal force is similar to static friction in the sense that its magnitude can change based on the situation. The difference is its direction can never change. It's perpendicular to the surface. So once I know the surface, the normal force is going to be perpendicular to it outward from it supporting it. So it'll never be inside the wall. But its magnitude can change based on the applied forces. So in this case, it'll grow as F grows. My second equation changes because now my Fs max direction has changed. So that becomes F max times sine of 40 minus Fs max, which is mu s times n, which is 0.4 times n, minus w equals 0. So previously I had a positive sign for this mu s times n over here, and now I have a negative sign because it switched directions from pointing up to pointing down. Okay, now as before, I just substitute the n value to be F max times cosine 40. So that gives me F max times sine 40 minus 0.4 times F max times cosine 40. All I've done is substituted F max cosine 40 for n minus 19.6, which was the weight of the book, equals 0. And once again, if I factor F max from the first two terms, I get sine 40 minus 0.4 cosine 40 equals 19.6. I've also added 19.6 to both sides. So finally, F max would be 19.6 divided by sine 40 minus 0.4 cosine 40, which your calculator will tell you is 58.3 or 58 Newton. There we have it. So any force between 21 newtons and 58 Newton will keep the book stationary. Any force less than 21 Newton will have the book sliding down to the ground. Any force greater than 58 degrees will have the book sliding up against the wall. This slice of physics gave you more practice on working with static frictional forces, as well as working with free body diagrams and solving problems using Newton's laws. Thanks for watching.